it's very important that you understand how a titration works. So I've got a picture over here of a titration. Now, we would have done some titrations if we had have been at school. So what happens is that you fill the burette with the acid or the base. So let's just read here quickly. It says that a titration is a method to determine the unknown concentration of a solution. Okay, so you'll have an acid and a base, and one of them you won't know the concentration of. The other one you will. Okay, the one that you know the concentration of would be called the standard solution, which is poured into the burette. So the standard solution is in the burette usually. Okay, so when you know the concentration, you pour it into the burette. Okay, now you saw how you read the burette, it's a little different. Okay, the solution of unknown concentration is sucked up through a pipette. Okay, so here's a pipette. You've seen them in my class, and I do have a pump for them at school as well. When I was at university, we had to just suck it up with our mouths. So sometimes we got a mouthful of whatever we were working with. Okay, and is then now this is a constant, and it's very often 25 milliliters. Okay, but it can vary. There's one graduated line, and you normally get a specific amount all the time. It says a very accurate way of measuring is in the pipette. So the pipette will always take the same amount. I have got some at school that have varying graduated marks, like a burette, but on the whole, the pipettes are have one single graduated line, and you only get one measurement that you can take with them. So it is quite accurate. Okay, so in this case they're picking up the base, and you will then transfer it into the conical flask. Now, as you can see, that the conical flask is used because when you swirl, it doesn't splash out. You've got to be careful about even the drops on the side of a glass. You saw how pedantic that guy was about cleaning. I remember doing that in analytical chemistry. We had to clean, I told you, 6 times with soap and rinse 6 times, and then you had to rinse with your solution, so you always had to make more than what you need. And then you put the indicator here. So because we're dealing with acids and bases, when you put the indicator in here, if there is a base in the bottom here, it will be the color of the base. As you are adding acid, in this case, the indicator starts to change. Okay, and when it reaches the end point, which we discussed yesterday with those indicators, you'll then get a different color, and you look for the specific color that you want. All right, so that is a titration. Okay, now so either solution can be acid or base. It just depends on which one you don't know. A few drops of indicator are added to the conical flask. The tap of the burette is open. Now, I have seen this before. It's hilarious. When somebody doesn't check that their tap is closed, and then they're pouring their solution in, but it's running out all over the floor. So I know I shouldn't laugh, but it's been funny. I remember that. And at varsity. Anyway, so the tap of the burette is open, and the standard solution is slowly added to the solution of unknown concentration. Once the indicator has changed color to indicate the solutions have been neutralized, remember, neutralized does not mean that the pH is neutral. It just means that the two, the amount of acid and the amount of base added is the same. But remember what happens to that salt that is made because of the acid base, that can change the pH. Okay, has reached its end point or equivalence point. So it's with the acid and base, the concentrations of the acid and the base are the same, but the pH is not necessarily 7. All right, so the following information can be determined by the experiment. So first of all, you're going to get the 2 volumes, okay, because you are going to measure a fixed amount, you're going to measure a fixed amount of volume with the pipette, so you're going to know your unknown concentration volume. Your unknown concentration solutions volume. You are then going to, when you get to your endpoint here, you're going to stop, obviously, the tap, and you're going to close the tap, and you're going to then take the readings. Now, what you normally do is you take your final reading minus the initial reading, and you get how much what your volume is that you reacted with, and that's how you get that volume. So your standard solution volume and your unknown concentration. You then have your concentration of your known concentration or your standard solution, and the most important thing here is that you have your mole ratio. So you do have a chemical reaction that you can work with. Now girls, you'll see in the textbook there is a thing that looks like this. Oh my gosh, I can't remember what it says. Oh my gosh, I can't remember because I never use it. You'll see it in the textbook. It's another formula that they use. Oh, why can't I think of it? It's based on C is equal to N over V. So it's the number of moles times the concentration of the acid over the volume of the acid is equal to the number of the moles, something like that. Okay, we don't use it. Okay, it's not a nice way to do it. If you like forget the formula like I've just done, then you are pretty much screwed, and you don't need that formula. In fact, the IAB discourages that formula. Okay, and it just confuses the issue. You girls know exactly what to do. You know, and you know your stoichiometry, and you can do it with stoichiometry, so it's much easier. You don't have to confuse the situation by learning another formula. Okay, you'll see it. It's a common one that they use in GDE, but I'm really going to discourage you from using it. Okay, so the only thing I want you to look out for is your centimeters cubed to decimeters cubed. So in this case it says, so I'm going to go 1 2 3, so 0,015 decimeters cubed. Okay, so 15 centimeters cubed or 0,015 decimeters cubed divided by 1,000 of a solution of calcium hydroxide. I think that's supposed to be if concentration of 0,01, so that's all here, is titrated with 30 centimeters cubed of HCl. So 3 decimeters cubed HCl solution. Determine the concentration of the HCl solution. So just like stoichiometry, let's just write out our formula, and it's balanced, so check that first. Okay, so I have a volume over here of 0,015. Maybe I must change this to another color so you can see. So I'm just writing out, remember how we do it, underneath each compound that we have, I have a concentration of 0,1 mole per decimeter cubed. Remember, if you can't remember if it's decimeter cubed or centimeter cubed, take a look at the concentrations. Even on your data sheet, they'll give you some sort of concentration, and you can see it's decimeters, so then you know to get it to decimeters. All right, so can you see here, it's easy to get our number of moles here. And then for our HCl, I'm just going to use it. Oh, my cat's back. We are going to use it here, and our volume is 0,03 decimeters cubed. Now, I need to get the concentration, but the first thing we're going to have to do is get our moles. How are we going to get our moles? Well, we're going to take it from there, and we can see it's a 1:2 ratio. So 1 to 2, and that's how we're going to get those moles. Then we can work out the unknown concentration. Okay, so N is equal to C is equal to N over V. It's funny how minds work. Okay, I can only do this. Oh, now my kids are playing and fighting. Okay, so N is equal to C times V, which is then 0,1 times 0,015. Okay, here's right, 0,1, oopsie, 0,1 times 0,015. Okay, and I get number of moles is equal to 1,5 times 10 to the minus 3. Please check me, you know how this works. So now I'm going to get those number of moles by using the mole ratio. So it's a 1:2, so we just times that by 2. 1 times 10 to the minus 3 times by 2. Oh gosh, sorry, that went completely haywire. Okay, 1.5 times 10 to the minus 3. I'm just going to equate it. times 2. Okay, and it is what you think it would be, 3 times 10 to the minus 3. Now we can get that by going like that. Yes, Jasper. And we divide it by volume. Yeah. And the concentration of our HCl is 3 to the minus 3 divided by 0,03, and I get 0,1 mole per decimeter cubed. Oopsie, I don't know what I was doing there. All right, so that is the concentration. So I want you to do it like you do stoichiometry. Nothing new for you to learn. That's why I don't like this, because there's no need for another method. You know how to do stoichiometry. Just use what you've got to get it. Okay. All right, so let's take a look here. So neutralizing, if you have a strong acid and a strong base, you're going to get a pH of 7. Why? Because your salt is going to be a pH 7. Strong acid with a weak base, you're going to have an acidic salt. So you're going to have a pH less than 7. And then a weak acid with a strong base, you're going to get a pH greater than 7. Okay, now it says your appropriate indicator. So if you look back at this table that we did yesterday, I'm going to ignore all of them except phenolphthalein, bromothiol blue, and methyl orange. Now again, you don't need to learn these off by heart. They will give you a table, and they'll probably give you ones that you've never heard of. But as long as you can see this. So we'll see here that at neutral, this changes. At 7 is bromothiol blue. So according to our one, bromothiol blue is an appropriate one for that. Okay. Here, if it is less than, you'll see it changes in an acidic here is methyl orange. So methyl orange would be the appropriate indicator to use for this titration. And then the last one would be for anything greater, and you'll see phenolphthalein will be the most appropriate because it changes at 8. So phenolphthalein. So basically what you're looking at is you're looking at indicators that will change in a base and change in an acid and change at neutral, and you pick them accordingly. Right, so predict the approximate pH and the suitable indicator for this. So this is a strong acid and a weak base. I think we only said group 1 hydroxides we are going to consider as a strong base. So if I remember correctly from the SAGS document. So this is going to be acidic. Okay, and we're then going to choose the methyl orange. Okay, ethanoic acid, NKOH, this is going to be basic. And obviously we're going to choose the phenolphthalein. And then the 2 here, this is a strong acid and a weak base. So again, we're going to have an acidic, and we're going to choose methyl orange. All right, so again, these aren't, these indicators are not limited to this. And they will probably give you ones, like I said, that you haven't really heard of. And then you would use this in the titration that you're busy with. I hope you understand all of this. Let me know if you're not.